In this video I'll be starting off with how the AC generator works, and for that I have this video here, and all you need is just see this video here and you should know your right hand thumb rule, and I'm sure you'll understand it. Firstly, some parts of it are a bit tricky to understand, and so I'm going to tell you uh, in a bit more detail when those parts come. But for now, we're going to look at this part by part. So I'm going to pause it when right now. Okay. So you can see here that the black arrows depict the motion of this whole conductor. The blue vertical lines with the arrows pointing downwards, this is your magnetic field. And uh, actually the induced current direction is also given here. You can't see it, but it's good because that's what we need to find. So we're going to do that right now. So I'm going to draw what they've given here. Say you've been given this diagram here. Now all you need to do is apply your right hand thumb rule, which is here, and find the direction of induced current. So magnetic field is downwards. Your motion of conductor is, where is it? It's to the left. Just imagine that you're looking at it from over here, somewhere over here near this yellow knob over here. So this is, and we're taking into account the top wire here, not the bottom one, the top one, the top part. So it's going towards the left. Now just extend your three fingers, match them. I should label it for you. This is B, which is magnetic field, which needs to be a forefinger, and the motion, which is your thumb, is towards the left. So if you do this, you'll see that your middle finger, which is induced current, will point towards you over here. So, and we also said that imagine that you're next to this yellow knob, you're looking at it from there, and we're taking the top wire into account. So you can see here, I don't know if you can see clearly, but there is an arrow that's pointing in this direction. It's like this. It is like this. And so I think you can also find out uh, what will be the direction in this wire at the bottom. You can guess it, it will be this way. You can try it out yourself right now. You can pause it and try it if you want. So this is how it is. Now I'm going to let you just observe the video for a minute. Not literally a minute, but just concentrate on this portion. Let's say in this, yeah, let's name this AB. Let's name this CD. Just you can choose A, B, or C. Just choose any one of them, and just pay attention to the arrows. Which just concentrate on this wire, or say this wire, whichever one you want. Just choose anyone and concentrate on the arrows, the red arrows on it, which indicate the direction of the current. So I'm gonna play it for about 20 seconds. Just notice the red arrows on it. These are the ones I'm talking about. Just notice if you see any change. Okay. So if you let's take the wire on top right now. Let's say it's AB. So let's play it. You see that here the direction has actually changed. I'm going to play it again. Just follow this wire as it moves around. It's all fine so far. There you go. It's changed. It's coming on this side now. Play it again. It's changed again. So you can see that whenever the conductor is in a horizontal position, the direction of current will change, and that forms the basis of this alternating current. Now the reason, of course, I'm going to give you right now, but say you have A, B, C, D. A here, B, C and D. Now say your current is moving like this. Initially, your magnetic field is uh, sort of going into the paper. Just imagine this situation right now. Now, this is actually, you could take this diagram that I'm drawing right now as the general form of the diagram. This will always be like this. I'm going to open the video again and tell you why. Let's take this situation over here. Now, if you look at it, the wire at the bottom, the magnetic field lines are always going to be pointing towards the bottom, and the motion is always going to be towards the right. So the current in that wire, don't just forget about the naming of A, B, C, D, but in the wire that is below, the current will always be going like inwards. If you put out your three fingers, you'll see how. And similarly, you can say for this top wire over here, it'll always be coming like towards you. So, irrespective of how you're naming it, that's always going to be the case. So, let's take the first case. Just minimize this. You have the current going from A to B, then to C, and then finally to D. Now, when this goes through one whole rotation, we noted that the direction of the current changes in the wire. That is, when say you're concentrating on AB, what will happen is AB will actually become like this. Now compare it to the general form, which is here. Now for AB to be like this, we know that it will come on this side. It will come on the right side of the conductor. And that fits in because we notice that every half circle, every half rotation rather, it changes direction. So this will become C and D. And so at this point, your current will be DCBA. So you can see that after half rotation, your direction of the current has changed from ABCD to DCBA. And that's all there is in AC generator. There's nothing else to it. This is all you need to understand. Uh, the rotation, the direction of motion will always remain the same. Your B, that is the direction of the magnetic field, will always remain the same. So in a particular part of the wire, the induced current will always be in that direction. And as your wire rotates, your direction, your AB is going to come into that position one point, and then after half rotation, your CD will be in that point. So if you look at that, the direction is reversing. First it's ABCD, then goes to DCBA. The next half rotation comes back to ABCD and then DCBA, so on. So you can see that this is why we call it alternating. AC stands for alternating current. Alternating current is the one in which your polarity keeps on changing. So one moment it's positive, the other moment it's negative. And you have something called frequency, and that is just how many times in 1 second uh, do you have a plus, or how many times in 1 second do you have a minus. So that's all you know under AC. And now, if you look, just concentrate on the graph that they've also provided here. I'm going to play it, pause it here. Now you can see that it's nearly the minimum when it's coming towards its vertical position, and here it's maximum. So your maximum EMF value and your minimum EMF value will take place when your conductor is horizontal. Sorry, vertical, not horizontal. When you have your conductor like this. The reason I'm going to give you right now, and for that I need to make a bit of space on the screen. Okay. Now, if you remember, I told you that what Faraday said was that the magnitude of the induced EMF depends on the rate of change of flux, really, the magnetic flux linked with the conductor. So let's draw the magnetic lines as the green lines here. Now let's take red as your first position. Just assume that at first your conductor is like this. It's lying horizontally. Number of field lines it's cutting is 3. Sorry, 4. Sorry, not 3, 4. Right. Now assume that it rotates a bit, and let's make it a lighter shade now, just to show the difference. You can see that it's still 4. Again, I'm writing 3. Sorry for that. 4. Now, when this becomes even, the angle becomes even more, it becomes something like this. And so it still remains 4. If you extend this green line here, you'll see it'll be 4. Now, as we come closer to the vertical position, say this is another position now. Again, this will eventually meet. It might be 3 or 4, that doesn't matter. But the point I'm trying to make over here is that, let's make this even lighter. So eventually it'll reach something like this. And here the number of field lines it's cutting is 0. Even if you take this number as 3, it'll prove my point here that the rate of change of magnetic flux is most between these two over here. Okay, the rate of change, this is all the same time. The time between this and this, this and this, this and this, and this and this, these are all the same value. So over here in this same time period, between the last two you're cutting 3, between the second last and the third last you're cutting 1, and after that you're all cutting 0. So you can see that the rate of change will be maximum here, and that's why when we draw the graph, say this is the alternating current graph, your so your maximums, one over here, one here. I'm calling this maximum because the value of this will be the maximum, except it's negative because its direction is opposite. These will both be when your conductor is lying vertically like this. And so also, if you look at this example again, at this point in red, you're cutting 4. At this point in orange, you're cutting 4 over here, you're cutting 4 over here, you're cutting 3. But at none of those positions will it be maximum EMF. They'll all be here, somewhere here on the graph. Right? And that's the reason that Faraday gave, that it doesn't matter how many field lines you're cutting, what matters is the rate of change. So you can keep your conductor cutting 500 lines also, but if you're not changing it, then there's going to be no induced EMF. So your maximum is going to be between these 2 points, which is why even if you have 0 lines being cut, that doesn't matter. Your induced EMF will be maximum. That's only because the rate of change will be the maximum. So that's all you need to know under the working, and I'm going to continue the advantages of alternating current over direct current, and then move on to transformers in the next tutorial. So that's it for now.